Now I want to spend some time relating Gibbs free energy to equilibrium. So, is the following reaction spontaneous at 298 Kelvin? This is barium carbonate becoming barium oxide and carbon dioxide. And so this is very similar to a reaction we've already seen. It's going to be the reverse of the formation of barium carbonate. And so if the formation of barium carbonate, this is the reaction that we had looked at previously, if that is spontaneous, then the reverse process, taking that product and turning it back into what was the reactants, has to be not spontaneous. And so how this is reflected in a Gibbs free energy is that the sign of delta G changes when you swap the direction of a reaction. So if you do the reverse reaction. So in much the same way that if a forward reaction is not spontaneous, then the reverse reaction is spontaneous. Another way to say is that the K goes from being reactant favored to product favored or vice versa. And so, the sign of delta G tells us the spontaneity. And so when delta G is negative, the reactants tend to become products and the reaction is spontaneous. When delta G is positive, we've previously said that that means that your reaction doesn't happen, but really just that forward reaction doesn't happen. But the reverse reaction is spontaneous. Those products that you've identified would turn into those reactants. And so we know that when you mix, say, chemicals together, both the forward and reverse reaction can happen and do happen and when you reach equilibrium, but one side is favored, right, by your equilibrium constant, right? Both the forward and reverse reaction are happening to some extent, but you end up with more reactants or more products. And that is described or kind of controlled by our equilibrium constant. And so the value of the equilibrium constant is directly informed by the value of delta G. And so overall, delta G negative corresponds to a spontaneous reaction. That would also be a product-favored equilibrium where K is greater than 1. On the flip side, if delta G is greater than 0 for your reaction, that means reactants will not become products, but products will become reactants. And so your equilibrium constant is less than 1, and it's a reactant-favored equilibrium. The actual equation we use to relate equilibrium constant to delta G is right here. Delta G is equal to negative RT ln Q, where R is, again, our gas constant that we've used previously. So let's look at an example. What is the equilibrium constant for the following reaction at 298 Kelvin? I have 2NO2 becoming N2O4.
All right, so what is the equilibrium constant for the following reaction at 298? So in a vacuum, we've seen that we can use equilibrium constants to do a lot. We know that it's really useful to have the equilibrium constant for a reaction because it lets you understand how much reactant and product is going to be present at equilibrium. It lets you make predictions on amounts, which is one of the things we really want to be able to control as chemists. How much product will I get because I want a lot, or how much product will I get because I do not want a lot, right? Those sorts of calculations, that sort of understanding is what we want to be able to do. And we want to ideally be able to come up with that equilibrium constant for any reaction. 2NO2 becoming N2O4, right? I just want to know this information. And so what we can use is we can use the fact that delta G is going to be negative RT ln of your equilibrium constant. So delta G describes the spontaneousness of a process. Do these reactants become products? And K is your equilibrium constant. Do the reactants tend to become products? Where is kind of the balance when you reach equilibrium? So these two things are describing similar ideas, and they are going to be related. The values are related mathematically. So if we want an equilibrium constant, we can get from calculating delta G. We can calculate delta G from our reference thermodynamic data. So the reaction is 2NO2 becoming N2O4. Delta G would be delta G formation of N2O4 minus 2 times delta G of formation of NO2. So N2O4 down here, N2O4 delta G is 99.8 kilojoules per mole. Minus 2 times NO2 is 51.3 kilojoules per mole. Put those together, we get negative 2.8 kilojoules per mole. And so we can always calculate delta G for any given reaction if we have the reference data. You can always look up the reference data, unless you're doing like cutting edge chemistry, coming up with molecules no one's ever made before. I promise there's plenty of reference data out there. And so you can always look it up, figure out what the delta G is going to be, and figure out then the equilibrium constant. So in order to do this relationship, we are going to need to do a little bit of algebraic manipulation, because we're going to plug in the delta G. What we want is this K, this equilibrium. So we're going to need to do some algebra. We have that delta G is equal to negative RT ln of my equilibrium constant. And I want to isolate out the equilibrium constant. So the first thing I'm going to do is I'm going to divide both sides by RT. So delta G naught divided by negative RT. I'm just going to move the negative out front. Is going to be equal to the equilibrium, natural logarithm of the equilibrium constant. And so I want the equilibrium constant, so I need to get rid of the natural logarithm. I do that by raising both sides as exponents of E. So I would have e to the negative delta G over RT is equal to e to the ln K equilibrium. E to the ln of something is just that something. So overall, I'm going to end up with the equation that the equilibrium constant is equal to e to the negative delta G divided by RT. And so that right there is going to be my equation. These two expressions imply the exact same relationship. I've just rearranged the equation basically to account for kind of basically what I kind of want to isolate. If I'm given the equilibrium constant, just plug it in here, turn it into delta G. If I'm given delta G, plug it into here, I can get the equilibrium constant. So what we're going to do is we're going to take this value we computed, we're going to plug it in. E to the negative delta G over RT. So on first blush, when we plug it in, we get E delta G is negative 2.8 kilojoules per mole, divided by R is 8.314 joules per mole Kelvin, times the temperature is 298 K. We're using temperatures in Kelvin. And so one of the things that we can see, which we've seen again and again here, is that kilojoules and joules we need to be mindful of. And we need to be mindful of those two values, that those need to line up. One thing I also want to note, there's a negative in front of here. Delta G is also a negative value. So that wasn't really clear. I see how I was writing it earlier. So this negative comes from right here. That negative comes from the value for delta G. And we need to deal with these energy units. So it's again just going to be 2,800 joules per mole divided by 8.314 joules per mole Kelvin times 298 Kelvin. So one of the things that we can see that we always want whenever we're taking an exponent of taking something as an exponent or taking log, all of the units better cancel out. So joules, joules, mole, mole, Kelvin, Kelvin. We want all of our units to cancel out. This plus negative sign cancels that negative sign. This is basically just, this becomes, you do some arithmetic, take e to that exponent, and you get 3.1. So we calculated that delta G was going to be negative 2.8 kilojoules per mole, and the equilibrium constant is 3.1. So both of those describe the same idea. When you do a reaction of NO2 to N2O4, trying to do that reaction, do the reactants become products? And this negative sign implies it's spontaneous. Not very spontaneous. That delta G is not very, very negative. And the equilibrium constant is greater than 1. So these are consistent with each other. Again, not very much greater than 1, which is consistent with not super negative answer we got right here. But this is really, really big. Equilibrium constants let us do a ton of things, right? They let us do calculations to figure out how much product or reactants or everything will be present at equilibrium. And we can figure out equilibrium constants of any reaction just by looking at tabulated data, which is really going to open up the ability to understand and study and use any chemical reaction we are potentially interested in.
So one of the big takeaways is that if you are given a chemical equation, you can calculate delta G from reference values, which you can use to determine the equilibrium constant, which you can use to figure out how much of your reactant and product will be present at equilibrium, how much product you will get, how much reactant you will have, all that kind of stuff. So we can truly and completely predict any chemical reaction that we want by using our reference values for delta G that we can look up to calculate delta G for a reaction. And so one of the things we want to look at, kind of figure out about these things is that delta G, we want to be consistent. Delta G was less than 0. It was this negative right there, negative 2.8 kilojoules per mole. And K was greater than 1, meaning it's spontaneous. So both of those values are indicative of a spontaneous process. One thing you'll note is that the delta G is not huge. It's not very negative, right? Negative 2.8 kilojoules per mole is pretty small, consistent with the fact that this K isn't huge. It's 3. So yes, it's product favored, but it's not very product favored in much the same way that yes, it's spontaneous, but it's not very, very spontaneous.
Participation 327, question 3. The Ka of HF is 6.3 times 10 to the negative 4th. What is delta G naught for the following reaction at 25 degrees Celsius? It's HF aqueous plus H2O liquid becomes F minus aqueous and H3O plus aqueous. This is the third question on participation 327 due Friday, March 27th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, the Ka of HF is 6.3 times 10 to the negative 4th. What is delta G naught for the following reaction at 25 degrees Celsius? It's hydrofluoric acid reacting as an acid with water to make fluoride and hydronium.
All right, so we want to talk about some of what we can kind of play around with in this equation when we're using delta G. And we can functionally kind of use it to look at overall reaction mixtures and reaction quotient. So, we know that at equilibrium, your reactants and product concentrations combine to give you the equilibrium constant, and you have nothing going on, you're just kind of locked in. But if say you're at some different mixture, you're at the equilibrium, you're at, described by your reaction quotient, you're not at equilibrium, you can calculate some sort of change in the Gibbs free energy to reach equilibrium. So this is the change in Gibbs free energy when you go from reactants all the way to products, whereas this is the Gibbs free energy of changing from not at equilibrium to being at equilibrium. And a system or a reaction mixture approaching equilibrium is always spontaneous. It always just happens. You don't have to push it. And so that means that delta G should always be negative. It's basically describing how out of equilibrium your system currently is and that it's going to go there. And so when we can see that when Q is and so we can kind of compare these values and put them overall into a plot. And we overall can see basically this is all reactants over here. Here's all products. And so this distance right here is this kind of delta G of the overall change. But, at equilibrium, you instead get somewhere like down here, right? And there's some sort of mixture where you have some kind of reactants and products. And it's actually at a lower Gibbs free energy. And so one of the things we can understand that basically the reason why you never fully convert to products is because you have more entropy if you have a mixture of reactants and products. We haven't really talked too much about the idea of mixing, but if you have both reactants and products present, there's inherently more disorder. If you transformed reactants all the way to products, you would have more information. Your system would be less disorder. There's less kind of variability. But if even one of your molecules is something else, right? It's still reactant. That is a huge amount of disorder because which molecule is it, right? If you have two of them, which ones are they, right? And so that's why you're never going to fully convert to products. It's all because of entropy. You always have a higher entropy to have some mixture. And so, if there's kind of a really big jump here, if this is a huge jump from reactants to products, then this kind of shift over to a little bit of reactants will be really small, and kind of the less the overall change from reactants to products, the more actual mix you see at equilibrium. And the opposite would be true when you're increasing delta G from reactants to products. If that's a huge jump, then there's really not going to be many reactants left. But there will be some always there to that kind of aspect of a little bit of entropy. If you got a little bit of mix, there's a little bit of disorder.
All right, we had another participation question in this video. There's only one more video in the set. Looking for any more participation questions there. I'll see you in that video. Bye.